Okay, hey everyone. Sorry for the sudden cut in the video. My Wi-Fi went down for a good 5 hours today, so I could not record the rest of this video, and it just suddenly cut out. So now I'm back to finish the recording, and hopefully I didn't miss anything with the recording at all. So I believe I was just talking about the example here and was saying about how when the p-value is 0.0489 and we use the significance level of 0.05, we're able to reject the null because the p-value is less than alpha. But when we use an alpha of 0.01, we cannot reject the null because the p-value is greater than alpha, which when we can't reject the null. So I think that's where I stopped. So I'm going to do this second example, and hopefully I didn't miss anything with recordings. So this second example is similar to the last one, but it has a little bit of a twist where it says that this is a two-tailed test here. So in the last example, we just had a left-tailed one, so that's just a one-tailed test. But in this next example, we've got a two-tailed test. And we know the area in one tail is 0.0084. But when we're finding the p-value, we want the area in both tails if it's a two-tailed test. So if it's a two-tailed test, you want the area in both of them. And we know the area in one of them is 0.0084. So in order to find the area with both of them, we just need to multiply that by 2 in order to get the p-value. So our p-value is equal to 2 times 0.0084, which is equal to 0.0168. Okay, so that's our p-value, and that's because it was a two-tailed test again. And so now we want to see how that compares to our two different significance levels. So first, let's do if alpha is 0.05. So our p-value is 0.0168. And this is definitely going to be less than 0.05, which means that at this significance level, we reject the null. All right, and now we're going to do it at the next significance level when alpha is 0.01. So 0.0168 is sadly not less than 0.01, which means that we can't reject the null. So it's pretty straightforward. If your p-value happens to be less than alpha, you reject the null. If it's greater than alpha, you can't reject the null. So now that we've done that, let's take a look at the example that we did before with the traditional way of hypothesis testing. And now let's just do it with the p-value method, and then we can see the difference between the two methods here. So it says to compute the test value and find the p-value. We already have the test value. We did it above, but I'm going to write it down just so that you see where this is coming from again. So we did this above when we first did the example, but just remember that the test value is z equals x bar minus mu over sigma divided by the square root of n. And in our case, x bar is 44,370, and mu was 43,000. And then our standard deviation is 5,230, and we divide by the sample size, which is 30. So when we computed this, we got 1.43, hence z equals 1.43, but I just wanted to remind you where that number came from. So when we're computing the p-value, I'm going to draw the picture for you so you can see what area we want. So if we draw our normal distribution here, so our value is, let's just say like right here. So we want the area that's in this tail. That's what we want. So we know how to do that because we've done that before using our charts. So remember that our little chart or table that we have gives us the area to the left of a z-score that you put in there, but we want the area to the right of it. So whenever we want that, we just go to the chart, find the value, and we just subtract it from 1. So I'm going to do 1 minus whatever my chart tells me is the area associated with 1.43. So let's go to our little part here. Okay, and I'm going to come to 1.43. Sorry. Okay, there we go. So at 3 and then 1.4, these intersect at 0.9236. Okay. So I'm subtracting from 1, 0.9326. And that gives me 0.0764. Okay, perfect. So this is our p-value. So we have a p-value of 0.0764. Awesome. And now we just have to see how that compares to our alpha or our significance level. So the problem tells us that our significance level is 0.05, and our p-value is 0.0764. Well, our p-value happens to be bigger than alpha, which means we can't reject the null, which this might be what you expected, because when we did the example the other way with the more traditional method, we also got that we couldn't reject the null. So this shouldn't really be a shock, but this is just a new way to figure this out. And like I said, this way is a little more commonly used, so we'll probably tend to use this over the traditional. So per request, I did get asked if there was any way that I could incorporate some like Excel or some R. If you don't know what R is, it's a statistical programming language, essentially. Unfortunately, I can't incorporate R into this class just because we don't really have the time. With a programming language comes learning a lot of like rules, and if you've never programmed before, that's a big task. So I don't want to give anyone the stress of doing that. Since it's not like part of our curriculum in this class. But I love the ambition of wanting to learn R because I do know R, but I just unfortunately don't have the time to incorporate it. But there is a way on your calculator to find the p-value. So I thought I would go ahead and give you a little tutorial on maybe how to do that. So that's kind of a way that we can incorporate some technology. So I'm going to give you a tutorial of doing that. So let me just bring my calculator up. Sorry, my screen's being all funky. Oh my goodness, it does not want to do this. Okay, whatever. Let me make this one a little smaller. Oh, it won't make it any smaller. Okay, that's fine. Okay, so let me show you with our example here. Okay, so if you have your TI-84 or something similar, follow along. So first of all, we are going to hit the stat button. And then you can see along the top, you have edit, calc, and test. So we're just going to come over to test because we're doing a form of a test here. And we are doing a z-test. So you're going to hit number 1. Cool. And then you can input your stats. So you want to make sure that it stays on the stats thing. And if you come down, I think I already put in all the values. So like for mu, you'll see that I put in 43,000. So that's good. For the standard deviation, I put that in 5,230. And then for X bar, 44,370. And then for N, I put in 30. And then this is where you have to pick what kind of test you're doing. So you have to pick if it's like, the right tail, left tail, or if it's two-tailed. So I went ahead and put that in. And then if you just come down, and then if you just hit enter when it's over calculate, you'll see it come up with all these values here. So it tells you what the Z score is, which is cool because that is 1.43, which is what we got, 1.43. And then it gives you the p-value of 0.0756, which you can see is very similar to what we have. So that is a cool way to do that on your calculator. I'm also going to do it with the t-test as well. So, which we're doing in the next section. So Just hang tight for that one. But yeah, that's how you do it with your calculator. So I'm going to do this one more time during this video, but not too bad. You really just need to input what you have, and then it's able to tell you that. So that's a cool way to use technology because yes, in like real practice, like no one's sitting here computing a p-value by hand, you know. So this is a good application. Okay. Okay, so that is it for section 8.2. So now that we finished the p-value part, we're going to move on to 8.3, which is going to cover using a t-test, and then we're also going to do p-value with that. So it's going to be pretty similar to what we did for the z-test, but now we're just using t-test. Okay. Okay, 8.3. Awesome. So like I said, we just finished the z-test, but now we're moving on to what's called a t-test. And if you remembered, like for the content for our last exam, we would use the z-test or the z-distribution when you know the population standard deviation. And then we use the t-distribution when the population standard deviation is unknown, which we talked about. That's a little bit more practical because a lot of the times you don't know the standard deviation for your population. So that's where the t-test comes in, because if you'll notice when we did the z-test, we had that population standard deviation. So it says right here, when the population standard deviation is unknown and the population is normally or approximately normally distributed, the z-test is inappropriate for testing hypotheses involving means. Instead, we will use the t-test when sigma is unknown or the population standard deviation, and the distribution of the variable is approximately normal. Okay. So recall from chapter 7 that the t-distribution is a family of curves and requires us to know the degrees of freedom in order to find the appropriate t-value. So just something to remember that we did have that extra thing that we needed to know when we were using our chart, which is the degrees of freedom, but that's not too difficult to calculate. It's just your sample size minus 1, which we will use. The t-test is a statistical test for the mean of a population and is used when the population is normally or approximately normally distributed and sigma is unknown. So good things to know if you're given a problem and you're not told whether you should use a t-test or a z-test, ask yourself, do I know the population standard deviation? It's usually the dividing factor here between the two. So the formula for the t-test is as follows. So we get t equals x bar minus mu over s over the square root of n, which if you remember, s is going to be the sample standard deviation instead of the population standard deviation. And then like it says here, the degrees of freedom are just n minus 1. So let's just clarify what each of these variables is. So first of all, x bar is equal to my sample mean. And then S is equal to my sample standard deviation. And then mu is going to be equal to my hypothesized population mean. And then n is going to be my sample size. Okay. And then we have how to find these critical values using your table. So we did this as well for the z-test, and we're going to do it again for the t-test. But now this is just using a different table because we're using that t-distribution. But it's the same table that we used for the t-distribution in the past, so it's still in that PDF that I gave you that has both the t-distribution and the z-distribution. Okay, so how to find your critical values. So first you need to determine if the test is one-tailed or two-tailed. And then you're going to determine the degrees of freedom. Then you will find the alpha level by looking in the appropriate row for the number of tails and down the column with the degrees of freedom. That might sound kind of confusing, but I promise it's not. And then it says, if the degrees of freedom is not in the table, always round down to the nearest table value because this is a more conservative approach. First of all, let's just do some examples. because sometimes the steps sound more confusing than they are. So first step is to find if the test is one-tailed or two-tailed. So our example says to find the critical t-value for alpha equals 0.01 with sample size of 13 for a left-tailed test. Okay, well, a left-tailed test is going to just be one tail. And then our degrees of freedom are going to be the sample size minus 1. So 13 minus 1 gives us 12. All right, so now we have those two pieces, and then it says to use our chart and to find the alpha level, which our alpha level is 0.01 here. So we're basically just going to take these three components and find what lines up with them. So I'll show you what I mean. So let me open my chart here. Okay, so this is our t-distribution chart. So we have a few things that we know. We know the degrees of freedom is 12. So that is right here. We also know that this is a one-tailed test with an alpha level of 0.01. So we're going to find where that's true. You can see that my one-tailed is right here. So I want that row. And I want an alpha level of 0.01, which is right here. Okay, so now I'm just going to see where these meet. So if I come across here, and if I come down here, that meets at 2.681. All right, so the number was 2.681, but because this is a left-tailed test, this is going to be on the left side of the mean on your distribution. So that means we need negative 2.681. And that's it. That's your critical value. So you just need to take the information you're given and find where it intersects on your little chart. Let's do two more just to get some good practice in. So this next one is the critical t-value for alpha is 0.05 with a sample size of 21 and a right tail test. So again, this is a one tail. And our degrees of freedom is one less than the sample size. So 21 minus 1 is just 20. And then we have our alpha level of 0.05. So let's put this all together. I'm going to come back to my chart. Okay. I will mark this up again with what we're looking for. Sorry, my tablet is not frozen. Okay, apparently I'm not going to get to erase that. Let's see. There it goes. Okay, so now we are looking at 20 degrees of freedom, which is down here. We are still looking at a one-tailed test, and our alpha is 0.05, which is right here. So this means right here, 1.725. I'm going to erase this, but we know it's 1.725. Okay, 1.75. And because it's a right-tailed test, we don't need to add a negative sign or anything. It just stays as positive 1.725. Okay, the last example is a little different because we are dealing with a two-tailed test. So that's our first thing that we notice is this is 2. And the other kind of big difference, at least, is the sample size is quite larger. So the sample size is 59, which means our degrees of freedom will be 58. So that's quite a bit larger than what we were used to before. And then we have an alpha level of 0.01. So let's go use our chart one more time. Okay, so we had 59 degrees of freedom. So if we scroll down, probably notice that there is no 59 on here. So if you look on our lecture notes, it says if the degrees of freedom is not in the table, always round down to the nearest table value. So 59 is not here, but we have 55 and 60, but it says to round down. So we're going to go ahead and go with 55. Because it says if it's not available, always round down. Okay, and then we're dealing with two-tailed. So this time we have 2, and we're looking at alpha is 0.1, which is right here. So this comes all the way down, and it meets at 1.673. All right, so we have 1.673, and then because it's two-tailed, we need 2 critical t-values because we need 1 on each side, but they're the same thing, just one's positive and one's minus. And that's it for finding those critical t-values. So similar to the z-test, you're just using that chart and the information you're given. Okay, so let's scroll down. Now we're going to talk about how to find p-values using the table. So this one is a little different, and I'm going to sneeze. Oh my gosh. Okay, finding p-values. What I was saying, this one is a little bit different than when we were using the z table or like the z distribution and whatnot. So there's a little bit different steps, and instead of getting a concrete number for this, we're going to get a range for the p-value. So we're going to get a range of numbers that the p-value can be between. A little bit different. So to find the p-value, 1, find the row corresponding to the degrees of freedom. And then you're going to find the 2 values in the row that the value of the test statistic falls between. And then you're going to look at the alphas that correspond with that, and those are the alpha values that the p-value is between. Okay, let's just do some examples so you can get some practice with this. So our first example here says to let n equal 29 and our test value be t equals 2.210. So we're going to find the p-value for a one-tail test and then also for a two-tail test. So we're just going to do both. But first we need the degrees of freedom. So our degrees of freedom is 29 minus 1, which is 28. And then we want to find the p-value for a one-tail test. And we're also going to be finding it for a two-tail test. Okay, so let me go to my chart. Okay. I'm going to erase what I have here. So our first step is to find the row corresponding to our degrees of freedom, and our degrees of freedom are 28. So that is this row. Okay. And then we want to find the 2 values in the row that our test statistic falls between. So our test statistic is 2.210. So let's see where that falls between. So we're looking at these values, and we want to find the 2 that our test statistic is between. So ours is 2.210, so that falls between these 2 right here. So 2.210 happens to fall between 2.048 and 2.467. All right, now that we found that, you just want to find the alphas that correspond to this. So if you scroll up, for a one-tail test, your alpha is between 0.025 and 0.01. And then for a two-tail test, it's between 0.05 and 0.02. So I'm going to go ahead and write those down. And like I said, for this one, we just get a range of values. We don't get a concrete value, but I will show you how in your calculator, when we do an example, how you can get an actual value. So for one tail, we know it's between 0.01 and 0.025. And then for our two tail, we know it's between 0.02 and 0.05. So it's just a range. It falls somewhere in between there, but like I said, if you use your calculator, it gives you an exact number. But I'll show you when we do like a whole example. Okay, so I did mean to change this problem down here and I forgot, so I'm gonna go ahead and do that. I'm gonna let n be 6. I'll change it on your lecture notes before I post them. And then I'm gonna change this to be 1.56. Okay, so we want to find it again for a one-tail test and for a two-tail test. Let's identify our degrees of freedom, which is 1 less than n, so that is equal to 5. And then we're going to be doing p-value for one tail. And we're also going to be doing p-value for two tails. Okay, so now we just need to go back to our chart and do that one more time. My tablet is really not liking to like erase everything. Okay, it does not want to erase my circle around 28. Okay, you're just gonna have to ignore the circle around 28. Sorry, it doesn't want to erase it. So our new degrees of freedom is 5, so I'm gonna circle 5. Oh, that's in white still. Okay, and then our test value is 1.567. So we want to look in this row and see what two values 1.567 falls between. And it happens to fall between this one and this one, which means that for a one tail, our p-value is between 0.10 and 0.05. And for two tails, it's between 0.20 and 0.10. I'll come back and write that down. Okay, so for one tail, we found it was between 0.05 and 0.10. And then for two tails, we found it was between 0.10 and 0.20. Okay, so that is how you find the p-value for a t-test. It's just a range, so a little different, but pretty similar in the process. Okay, so the last thing that I want to do is put all this to use and actually do an example. So we are going to do an example and kind of use like both the traditional and the p-value testing. I just want to talk about both of them. So let's just give it a go. Our example says, we wish to check that normal body temperature may be less than 98.6 degrees. In a sample of n equals 18, the sample mean was found to be 98.217, and the standard deviation was 0.684. Use alpha equals 0.05. Okay, so step one is to state your hypotheses and identify the claim. So let's do that. We're going to write our null and alternative hypothesis. So our H naught or H0 is our null. And our null is always that mu is equal to whatever like that number is that we might be assuming in the alternative one. So we're assuming that body temperature may be less than 98.6. So our null is that mu is actually equal to 98.6. And then our alternative is that mu is, is less than 98.6. And that is our claim right there. Okay, step two is to find your critical values from the appropriate table. So we need to know a few things. We did this at the very beginning. So we need to know if it's a one tail or two tail and what the degrees of freedom are, and then the level of significance. So the degrees of freedom is 18 minus 1, which is 17. We have that alpha is equal to 0.05. And we know that it's a one-tail test. because we have mu being less than something, not like mu being not just equal. So we have mu just less than 98.6 is our alternative. Okay, so to do that, we're going to go to our chart and figure out what this value is. See if I can erase this time. Oh, it really doesn't want me to erase that 28. Okay. All right, so we have degrees of freedom being 17. We have alpha equals 0.05, and it's a one tail. So we're going to see where that meets. And that happens to meet up at 1.740. Cool. So we have a critical value of 1.740. But because it is a left tail test, we want that to be negative. So if it's a left tail test, you want it to be negative. If it's a right tail test, it just stays positive. And we know it's left because we're claiming mu is less than something. So I'm just going to draw a little picture. So this is where my critical value is. And this is my critical region, if you remember talking about. All right, so next we're going to compute the test value and then also determine the p-value while we're at it. So our test value is t, it's a terrible t. T is equal to x bar minus mu over s divided by the square root of n, which is equal to 98.217. If you read the problem, it says that the sample mean of this was found to be 98.217, so that's where that came from. And then I subtract from it 98.6 because that is what I'm assuming the population mean is less than. My standard deviation is 0.684. And then I divide by the square root of n, and n is 18. And if you plug this into a calculator, you get negative 2.376. Okay, so before we actually do the whole p-value thing, I just want to remind you that when we did the traditional method of hypothesis testing before, we just calculated the test value and said, hey, if it falls within that critical region, then we're good, basically. So already right now, I can make a guess that I'm probably going to be able to reject the null hypothesis just based on what my test value is and the fact that it does fall within that critical region. But let's go ahead and do the p-value thing. So I'm going to determine like the range that my p-value might be between. So if you scroll back up and remember how we did that, we just need the degrees of freedom, and then we can find what it is for our one-tail test. Back to our chart. Okay, so our degrees of freedom, they are 17. And then our test value is 2.376. So we can see where that falls between. And it looks like it falls between these two. So if I come up here, I have a one-tailed test going, which means my p-value is going to fall between 0.025 and 0.01. So my p-value is between 0.01 and 0.025. Okay. So right after that here, our alpha level is 0.05. And remember, we can reject the null hypothesis if the p-value is less than alpha. Well, if p is between 0.01 or 0.025, automatically right now we have that p is less than 0.05, which is great because that means that we are able to, in fact, reject the null hypothesis. But like I promised, I'm going to show you using your calculator that will give you an actual p-value. So using your calculator, I'll show you what we get for the p-value here. Okay, I think I'm back. It completely cut out again, my Wi-Fi. So let me go back to sharing my screen. Okay, we're back now. So it should still be recording. Yeah, okay, cool. So I was just going to show you how we do it with the calculator. So I'm going to go ahead and hit my stat button again, and I'm going to come over to tests. And then I am doing a t-test here. Oh, shoot, sorry. I made a mistake. Sorry, hit your stat button, come over to tests, and then because we're doing a t-test, you're going to hit the 2. There we go. So then you can go ahead and input your data. So let's do that. So if I come down here, I want to put in whatever mu is. So in our case, that's 98.6. And then I want to put in my X bar, which in my case is 98.217. And then my standard deviation is 0.684. Right, and then my N is 18. Okay, and then just make sure that you have it on the correct one, which I think I need to switch it. I believe it should be this one. Okay, and then we just come down to calculate. Yes, and we're good to go. Okay, so you can see that here we have a what am I trying to say? The t-test value of 0.237, well, 2376 if you round, which is what we got when we did it by hand. And we got a p-value of 0.014. So let's write that down. Which is great because that does fall within our range that we have. So that is definitely between 0.01 and 0.025. So right on. So using both of those things that we did, we can say that the p-value is less than our significance level, which means that we can reject the null. So we reject. And then lastly, we just need to summarize our results. So I'm going to write up a nice sentence that really says everything in the correct statistical language. So our summary is, there is enough evidence to support the claim that the body temp is less than 98.6. Awesome. So we are able to reject the null hypothesis and we can accept the alternative one and say that we do have enough evidence to conclude this. So that is going to be it for section 8.3. So it's just on using a t-test instead of a z-test. Similar process, but just a different distribution. So now you have learned a z-test and a t-test with doing the traditional method and also the p-value method. You've learned how to reject the null. So that is all that I've got for you today. Hopefully this lecture video wasn't too long or too boring. So that is all. I hope you guys have a great Monday and enjoy your time not spent in lecture. And I will see you all on Tuesday. Bye, everyone.